All right. Welcome, everyone. This is the first lecture of the course called Mobile Health. And in this lecture, I will introduce myself, the team, the problems we're going to talk about, the way we are describing them, the assessment, the way we'll support you, and then conclude. So first, a little bit about me. I'm a professor of mobile systems, and I work in general on using sensing and wearable and coming up with new ways of sensing behavior and health, but also into analyzing the data that is coming from the devices that contain this sensor. We're also interested in making the systems efficient, given that the systems are often resource constrained. They are wireless and often not attached to a source of power. The data that comes out of these devices is often difficult to label, it's often scarce, it's also often noisy. And so data analysis and machine learning techniques to use on this data are often challenging and unique. And then I work on applications mainly related to health and diagnostics of this kind of sensor devices and sensor data. So what is mobile health? Well, mobile health tries to make use of the digital wearables that are already embedded in devices and sensors. And this is to proxy information about our behavior and our health to improve our way of diagnostics and progression. And that's because often devices offer quite good information about what we're doing without asking the user. And also sometimes in a scalable and very cheap way. So we'll see examples of use of these techniques in a variety of health settings and using a variety of sensing inputs. So each lecture will be relating a sensor mode to a set of applications. So why are we interested in using mobile and wearable devices for this, for mobile health in general? Well, it's scalable because these devices and sensors are often embedded in everything we take with us. I have a wearable here now. I have a phone here. I often wear a watch, and there are a bunch of devices also scattered around where I live. And so if we could use that, that'd be quite scalable already. It's often affordable because, in fact, it's much better to get data from these devices instead of sending someone to a doctor and having very expensive medical tests. It's continuous. It gives us an input that is often unprecedented. Because the device stays with us all day, like a microphone on my phone or the earbuds, they stay with us continuously. They can give a signal that is often unprecedented, especially for doctors. Sometimes I have conversation with clinicians and ask, what could you do if I give you an input of the person from this sensor continuously? And the answer sometimes is that it's unclear because they've never had that sort of input. Techniques developed from these devices is non-invasive. In the sense that the sensors are already there, we're already carrying the device. And if it proxies invasive tests to understand our health, for example, a camera shining on our skin to detect some blood conditions and blood level instead of puncturing the finger for a blood test would be really interesting, for example. Some examples of this already exist. And it's sustainable. Some tests are required to throw away a lot of plastic. Can we substitute them with a test that just uses a sensor and a device? That would be kind of interesting. But there are challenges, and that's why there's a full course on this. First of all, type of sensors. Some sensors are still being developed. This is not a domain that we will discuss much, but also using sensors that are already there for different purpose. For example, the first purpose of an accelerometer on a phone was to allow the user to play a game, tilt a ball on the screen to play a flipper game. However, it's a sensor that can tell a lot about the user behavior and user step count. Devices are often resource constrained, so the amount of data gathering and data analysis you can do on the device, or even sending data out of the device, is expensive. And so these constraints need to be considered when thinking of the algorithms for the analysis of the device. Now we'll talk about a concept that is sampling. How often do I need to get data from the sensor to make sense of this phenomenon, this diagnostics that we're trying to do? So the frequency of the data harvesting is important, mainly because for the above reason, we have a battery. We don't want to sense too often if its sensing is expensive. And also, this needs to be traded off with the ability to understand if the data is enough to give conclusions about the phenomenon, a diagnostic phenomenon. So this trade-off between how often, because of the battery, and how often because I need to understand the phenomena, is interesting. Then, of course, the location. This is again related to resources. The location of the pre-processing of the data. Data is noisy. It needs to be analyzed. Processing and pre-processing could be in different location. I can do all the analysis on the device if I have battery, if I have time, if the latency of this is not too high. Or I can send everything off the cloud. However, I need to consider my network for that. I need to consider how much of my connectivity, cost in terms of battery and latency again. And also in terms of cost, I might have a cap on the data. Data labeling is a very big problem in this sort of domain because coming up, and we'll see plenty of examples of this, coming up with labels of an activity. So, for example, if you carry your phone all day, then how do I know that that particular set of, again, accelerometer sample indicate the steps you're taking and which one are exactly the steps? So having good data for training that has the label has been difficult, so people have come up with solutions around the labeling problem. Data could be sparse in various sense. One is because perhaps you are only able to have certain examples of certain activity from the data. The user is not using the device properly, or we've not collected the important data properly, or there are gaps in between. And so it's quite common not to have very continuous data, at least for training. And so the signal processing machine learning for this data is challenging for the reasons said above. The elephant in the room here is often the privacy. This data, although quite not as obvious as in the case of a person's face and image, tells a lot about the user, especially, for example, the location. And so there are all these problems of how do we obviate, how do we still allow the collection of this very important data that you will see gives a lot out about the user behavior and user health, but at the same time, we need to protect the user privacy. And then linking the data to clinical outcomes is something we'll describe in some of the lectures too. So now you interpret and analyze the data. How do you link it to something that makes sense clinically, and possibly with certainty, right? So let's say the machine learning comes up with a result. How are we certain that this is the right outcome? And sometimes people have advocated for approaches that keep the clinicians in the loop when some of the machine learning applied to this data is not certain about the prediction. Devices, well, this is even already, every time I pick one of these pictures, 1 minute later, I found that it's an old picture already. And so this is an example of devices that exist already in our house, in our homes, that have sensors to sense our behavior. Some are examples of devices we carry, and some are examples of devices that are around us. And so this is the compound annual growth rate of connectivity and billion of connections happening in mobile data. So there's lots of data from these devices coming along. And so how do we use it? How do we make sense of it? Does it make sense to use it? And this is the other side of the coin somehow. Although this picture already has had already a few years, I find it quite compelling. So on the x-axis, you find different countries. And on the y-axis, the percentage of, this is just browsing sessions on network technology. And obviously in the US, it's all yellow and orange, meaning that the connection is quite fast and good. But if you go to different countries, this picture is different. And the last column, Nigeria, mainly has connectivity, which is much at higher latency than the US. This means that if we are planning to develop technologies that are really reaching the masses and reaching every corner of our population, we need to consider this image and consider that we can perhaps architect our system differently and better. So for example, sending less data, deciding when to send the data, consider paradigms of networking that perhaps you wouldn't consider if you were just considering the first bar. So phone sensors and radios. So this is an image of a Samsung phone this is a Galaxy 20, and it's from the back. And you can see various components. So these sensors, this phone is already more powerful than my first computer, which probably tells more about my age than anything else. But well, in addition to power and CPU, GPU, and coprocessor, there are additional sensors that we'll talk about in the lectures one by one. So there are inertial measurement units that allow to understand movement aspects of rotation as well as steps and speed. And there are location sensors, such as the Global Positioning System, GPS, that allows you to position a person quite precisely when outdoor. There are cameras, there are proximity sensors, there are microphones that allow us to use the audio for understanding something about the user. And there are a range of radios that, in addition to allow communication, we will see they also allow localization and contact tracing. So what is probably the most traditional use of mobile health is the use of mobile questionnaire, the ability to ask the user pen and paper like questions, but whenever you can send them essentially whenever you want, because the phone is in their hands all the time. So you can do quick questionnaires multiple times a day. You can personalize very quickly the next questions based on the previous questions, because this is an online experience. You could tailor the messages, you can tailor what the user is told. And in the last lecture of this course, we'll also show how by using the sensors on the phone, you could decide when to send a certain message and what type of message you should send for a behavior intervention approach. But I'll leave that for the lecture itself. Here is just to say that the basic use of phones and devices is simply a way to interact with the user, to get feedback, to get them to answer, what's your medical history, what are you doing now, And this already has changed the way we diagnose and check the progression of health of individuals. There's been a growth, obviously, in the number of medical apps downloaded during COVID. This is by country. This is, medical apps are simply sometimes a way for you to connect to a doctor. So having a Zoom session to a medical app, or for you to interact with a GP. But there are also examples of apps that collect data about your health, possibly often via questionnaire. And so in addition to devices that are around us, there is an emergence of devices that we wear and are attached to our body. The biggest examples that are out there right now are these things that I'm wearing, so earables, as I call them, and watches. But they're rings, and we'll have some examples of rings and some shoes tracker. And the watches themselves are coming out with more and more monitor. We will show examples of sensors that can monitor heart rate, sleep, activity, blood oxygens. Some of the devices now already do a one-lead electrocardiogram from the watch. And there are some suggestions already in the research community on how to do, for example, blood pressure. Well, I mentioned earables already twice. Some people have defined them as the next computing platform after the smartphone, because they think they will be standalone devices. But these sensors also allow the monitoring of health. There are a few papers already trying to do things from those devices. We're also working quite heavily on this, and I will give you some examples. But the research is not stopping there. The sensors woven into fabric that monitor vital signs. Obviously, at the moment, these are just quite dumb sensors that need to send their information to other devices. So another area of research is the area of combining simpler, cheaper sensors, possibly with limited batteries, with devices we carry, such as smartphones, so that it's possible to have a combination of the two and collect and harvest useful data. One thing I would like to spend some time on at the moment is how we measure performance on the system, on the data of the system. And I'm sure perhaps this first slide should be perhaps with all of you, something very familiar. This is a picture I've taken from Wikipedia about classification tasks. So there are two measures that are generally used in machine learning, precision and recall, and F1 score is a combination of the two, which is a ratio among the two. And the picture, I find this picture very useful. Precision measures of all the dots that, so these are the points that you're classifying. And so let's say that these are the solid dots are the one that are really, they should be positive, they are positive, so all the solid dots here. So the green refers to being positive. And here, the non-solid dots indicate negatives. These are negatives. The circle here indicates all the points that the machine learning methods defines as positives. And outside the circle is everything that the method decides to be negative. And so precision defines how many, so on the top of the ratio you see below is this green part, how many that on the bottom, so all of the ones that have been defined positives, how many of them were really positive? So how many of them did we get right of all the ones we defined as positive? Well, recall gives a different view and indicates of all the ones that are positive, so this fraction here, how many did we spot? Now, there's another way of seeing this. Here, the first picture is one that you know, and that's the one I just described. And this is some other two measures that are very, very used when we look at mobile, well, health data in general. They are sensitivity and specificity. Now, if you're quick, you would see the sensitivity is nothing else than recall. And so it indicates how many of all the positives that are out there, how many have we spotted with this test? Specificity is of all the negatives out there, how many have we identified as negative? So these ones these are the ones we have identified rightly as negative. These are the false ones. And so you will see that these two measures are very used. And why are they used? Well, for example, I'm sure you've heard that COVID tests have a sensitivity level. So let's assume there's a COVID test that has a sensitivity of 70%. What does that mean? So if you have, let's assume that we test 10 people that we know have COVID. So they all have COVID. So these are the big green part. And the sensitivity will tell you that 7, so if the sensitivity is 70%, you say that 7 would be identified correctly and 3 would be not identified correctly. Means that we are unable to spot them as positive. If the sensitivity was 80%, we would identify 8. Now, on the other side, specificity of 70% indicate that if we test 10 people that do not have COVID, so they are on the right of that image, the test would identify 7 as healthy and 3 as affected by COVID wrongly. So they'll have a positive test, but in reality, they are not COVID positive. In reality, the current antigen test has a very high specificity. So if you have a line, if you identify as COVID, it really means you do have COVID. So the identified wrongly as COVID is very minimal in the current antigen test. One other aspect is very important when we talk about general health data is disease prevalence. And I don't know how much machine learning you have done in your life, but often we work with somehow balanced test sets and balanced training sets, especially for binary tasks, it would be 50-50. However, often in disease prevalence, you would have something like 7%, 10% population having the disease out there. So you need to consider it when you're testing a system, that it might be that. And also sometimes if you train the model over a 50-50 healthy and non-healthy, when you try that model on a population that has a different balance of classes, you will find that that doesn't work. And so disease prevalence is one variable you need to consider when you use machine learning. There are also aspects that are important related to confounding factors. Confounding variables might produce spurious associations that are not really causal link from your data and your results. I'll give you an example. If you're trying to find a link between lack of exercise and weight gain, and you do find that your data says the lack of exercise leads to weight gain because of you train the model and you test the model and you say, oh, well, there's a link there. You find a correlation. But then you have not checked for a variable of perhaps diet, how much people eat. And it might be that in your set, the people who exercise a lot eat less than the people who don't exercise a lot. So all of a sudden, although you have a correlation, you might not have a causation there. It might be that the reason why they are improving, while they are gaining weight, might be due to diet rather than exercise. And you haven't proven really anything. So eating should be a control variable in this case if you're trying to find that link. Which means that in practice, what we do is that you would try to split the data so that people with the same, you probably use people with the same diet in both sets. Bias in the data collection can lead to the wrong conclusion and prediction. So if the data on which you train contains data from a predominant group, which means other groups are not able to be predicted well, that's a problem. I'll give you an example. Models of cardiovascular disease that claim to predict heart attack 5 years before are trained on male data sets. The prediction in women may not be accurate as the disease has different expression in women. And I'll give you another example. We've tried to work on prediction of COVID-19 with audio signal, meaning that we've collected, and I'll give you some more examples in the audio lecture. We have used a data set that collects cough, breathing, and people reading on the screen voice of the individuals. However, at that point, our classifier was very good. It turned out that we had training data that had Italians who had COVID and English who did not. And so our model was learning that if people were speaking English or Italian, then they could be distinguished. And so the bias by language was a little problem. And the solution was to find an architecture that could control for that language problem. Ethics. The data that we collect from these devices is sensitive, and ethics and privacy are always the elephants in the room. So the data is continuous, very personal, very revealing, easily collected and easily aggregated. And so what can be done apart from obviously applying for ethics applications to do clinical studies and clinical trials? The solution in practice for when the technology is deployed out there needs to be thought carefully, because we're collecting large masses of user data. So a device, an on-device approach to trying to do analysis on device could be very useful. Differential privacy is a word that is often used in practice to define approaches that send part of the data to the server for analysis, but doesn't reveal enough private information. Federated learning, also another word. We won't talk much about these approaches, but I'm just pointing out there's a need and a body of knowledge that is trying to exploit these to improve the way in which we use this sort of data. And so there are aspects related to how we develop the model versus what we deploy. And those are very important parts. So you can improve the way you develop the model to get privacy embedded, and a way in which you use systems aspects to deploy the model to be privacy and ethically acceptable. And now I will spend some time just describing a little bit about the course. So each lecture, apart from the first one, each lecture will concentrate on aspects related to one particular sensor. First, though, we'll have a primer on signal processing. And I'm trying to be inclusive of all the people that might not have had signal processing experience. Then we'll concentrate on the inertial measurement unit, and we'll link it to human activity recognition and health. And I will now introduce this very disruptive cat. His name is Alfie. He will feature in some of the other lectures too, I'm sure, and he will interrupt all my videos. He's a 15-year-old cat, 14 actually, 15-year-old cat, and he is a pain every time I try to record. Each lecture will concentrate on a sensor, and we'll have audio, we'll have PPG, which is the light shining device coming out the back of our watches. We'll talk about Bluetooth and GPS, and we'll then talk about contactless health monitoring. I've mentioned already that we have a behavior intervention lecture at the end, and that's the one where we try to use the information coming from the sensors to decide what to suggest to the user. And then we have 2 practical lectures and 2 guest lectures. The guest lectures are given by Professor Roberto Cipolla, will concentrate mainly on the video and imaging for health. And then Professor David Clifton, who has a range of experience in clinical mobile health. There's also a seminar series going on, titles still to come, but this is at 4 p.m. on Tuesday in FW26. Some will be online and all talks will be recorded. So please come along and ask me for more information later. The course assessment, there'll be 2 assessments based on the data sets. The first assignment is worth 30%, and it's about signal processing really and data cleaning and the basic analysis steps. And this is just be done through a report in Colab. The second assignment will be a fuller analysis and is split by type of course you're doing. Some will be more and some will be less, and the deadline will be at the end of the term. Information is found on the page, and we'll link other pages to this page. We will have support on Moodle where you can ask questions for the various assessments. And the team that is supporting you is including me, but also teaching assistants who are a range of senior research associates and PhD students. So Erica, Kayla, Jing, Ian, Sotiris, and Abub will be supporting in the various stages of your assessments. And for today, that's it. And thank you very much.